Bounds define the range within which a value is expected to lie. The upper bound is the maximum possible value within the range, and the lower bound is the minimum possible value within the range. An error interval essentially shows the range within which the true value is likely to be. For instance, for this one down here, 4.5 and then 5.5. So this 4.5 is essentially the lower bound. This 5.5 is the upper bound. And then this whole thing here is essentially the error interval. So when we talk about error interval, we're just showing the range of values this m can be. So let's look at this one here. 3.7 has been rounded to one decimal place. What is the error interval? So what we can do is we can write 3.7 in the middle. And then we work out what one decimal place higher than 3.7 is, which is going to be 3.8, and one decimal lower than 3.7, which is essentially 3.6. And then to work out our upper and lower bounds, so for our upper bound, we're going to work out what is halfway between 3.7 and 3.8, which is essentially 3.75. And then for our lower bound, we work out what is between 3.7, so the middle number for 3.7 and 3.6, which is going to be 3.65. So this here is our lower bound, and this one up here is our upper bound. So that means that our number has to be bigger than or equal to 3.65. But it has to be less than 3.75. And we have to say there has to be less than 3.75, because if we round 3.75 to one decimal place, because the 5 here is 5 or more, that means that we have to round up. So if we rounded 3.75 to one decimal place, we'd get 3.8. So that means that our number has to be less than 3.75. And the reason why it has to be equal to or more than 3.65 is because if we round 3.65, the number to the right of this 6 to one decimal place is 5. So that means we have to round up. And if we round 3.65 to one decimal place, we get 3.7. So that's why we have to say it has to be equal to, it can be equal to 3.65. Okay, this one here, 3.7 has been truncated. Very important. Truncated means cut off. Well, how I like to see it as cut off anyway, to one decimal place. What is the error interval? So, remember that truncate essentially means cut off, or how we know it as. So if we use the idea of it being cut off, that means that our value, so our range of values for this to be truncated to 3.7 to one decimal place, means that our number can be 3.7, but it has to be less than 3.8. So we have to write this sort of interval here. And the reason why it has to be less than 3.8 is because if we truncate 3.8 to one decimal place, we get 3.8. But if we have a number of 3.79999999, it doesn't matter what number is next to the 7, because we are only interested in the first decimal place, which is 7. When we truncate, we cut off. So we don't care what number is next to the 7. It can be 9s, it can be 6s, it can be 3s, it can be 2s. We essentially just cut it off. So essentially 3.7999999999 is going to be 3.7 when truncated to one decimal place. So that's why we say our interval has to be equal to or more than 3.7, but it cannot get to 3.8, because if we truncate 3.8 to one decimal place, we get 3.8, but we want to get 3.7. Okay, so this is an exam question, well, and sort of exam style question. So the mass of an apple A in grams is given as 80 grams. Give the error interval for A in each of these situations. So part A, when the mass was rounded to the nearest 10 grams. Part B, the mass was rounded to the nearest integer. Or part C, the mass was truncated to an integer. That is meant to say was, not been. Yeah. Okay. So let's look at part A. So first thing we do, highlight important key bits in the question. So yeah, mass of an apple, okay. Error interval, yeah, using A, so our A is going to be in the middle of our error interval. And it's rounded to the nearest 10 grams. So we can do our number line. So 80 grams in the middle. We work out what is 10 grams higher than 80 grams, which is 90 grams, and 10 grams less than 80 grams, which is 70 grams. So for the upper bound, we have to work out what is halfway in between 80 grams and 90 grams, which is going to be 85 grams, which is our upper bound. And then for a lower bound, we work out what is between 70 grams and 80 grams, like smack bang in the middle, which is going to be 75 grams. That is our lower bound. So, therefore, in error intervals, our number has to be, to the nearest 10 grams, has to be equal to or more than 75 grams. So A, but it has to be less than 85 grams. Okay, part B. So the mass was rounded, need to get rid of that, to the nearest integer. Okay, very important, nearest integer. Same thing that we've been doing, 80 grams in the middle. To the nearest integer means to the nearest whole number, so essentially the nearest one whole number. So one whole number higher than 80 is 81 grams, and one whole number less than 80 is 79 grams. To work our upper bound, we work out what is halfway in between here, which is going to be 80.5 grams. That's our upper bound. And then for our lower bound, we work out what is between 79 grams and 80 grams in the middle, which is 79.5 grams. That is our lower bound. Then our error interval, we're going to write 79.5. Yep, so A has to be greater than or equal to 79.5, but it has to be less than 80.5 if it has been rounded to the nearest integer. Okay, part C. So the mass of an apple A is given as, 80 grams, and now it's been truncated to an integer. Okay, so when we hear the word truncated, cut off. So first of all, we know that the lowest possible number it can be when truncated to the nearest integer, which means whole number, is 1. Well, 80. 80 grams is the lowest it can be. And then for it to be truncated to the nearest integer, to a whole number, one whole number higher than 80 is 81 grams. So that means that our A has to be equal or greater than 80, but it has to be less than 81 grams when we are talking about truncation. Okay, now we have another exam style question. So it says, consider the formula A is equal to F over M. F is equal to 45 to two significant figures. M is equal to 16.1 to three significant figures. Okay. By considering bounds, work out the value of A to a suitable degree of accuracy. Okay, that's very important. So let's do it. So let's work out the error intervals for F and for M. So let's look at F first. If 45 has been rounded to two significant figures, so essentially here, 45 to two significant figures, then that means that our error interval has to be between 44.5 and 45.5. Because if we round 44.5 to two significant figures, we get 45. But if we round 45.5 to two significant figures, we get 46, meaning that our number for F has to be less than that. Now let's look at M. So M, our 16.1, has been rounded to three significant figures. So 16.1 to three significant figures. So that means our lower bound is going to be 16.05 and our upper bound is going to be 16.15. Okay. So now we need to work out our upper and lower bounds for A. So A is equal to F over M. So when dividing, it's important to remember that to find the upper bound for A, we have to use the upper bound for F, divide by the lower bound for M. Because let's think about it. If we have like 100 divided by 2, so 100 over 2, for instance, gives a big number, right? Gives 50, which is a big number. If we do 100 divided by 50, So saying big number divided by, let's say, a big number, we get a really small number. So if we do a big number at the top and we divide by the smallest number possible, get a big number. If we do a small number at the top, divide by the biggest number that we can find, we get a small number here. So for our upper bound for A, we are going to do our upper bound for F, which is 45.5, divide by our lower bound for M, which is this one here, 16.05. And then for our lower bound for A, we're going to do the lower bound for F, so 44.5, divide by our upper bound for M, which is 16.15. Okay, so let's look at the upper bound. If we do that onto our calculator, we should get an answer of 2.834, so on and so forth. Then for our lower bound for A, we should get an answer of 2.755. Okay, so we've done the big bulk of the question. So now we need to do the last bit of the question, which is to find a suitable degree of accuracy. So what that essentially means is we look at the upper bound for A and the lower bound for A, and we try to round each of them to 1 significant figure, 2 significant figure, 3 significant figure, so on and so forth, to see where the upper bound and the lower bound match. And the more significant figures it is, the more accurate our answer is. So let's look at the upper bound for A. If we round the upper bound for A to 1 significant figure, so upper bound to 1 significant figure, we get an answer of 3. Let's look at the lower bound. Lower bound for A to 1 significant figure, we also get an answer of 3. Okay, can we try to make it more accurate by maybe doing 2 significant figures? So if we look at the upper bound for A, let's say to 2 significant figures, we get an answer of 2.8. And if we look at the lower bound for A to 2 significant figures, we get an answer of 2.8 as well. Okay, that's looking a bit more accurate. Let's see if we can round to 3 significant figures. So if we round the upper bound for A to 3 significant figures, we get an answer of 2.83. Whereas if we round our lower bound to 3 significant figures, we get an answer of 2.76. Do those two match? Do the upper bound and lower bound match? Are they the same? No, because our upper bound to 3 significant figures is 2.83, whereas our lower bound for A to 3 significant figures is very different, which is 2.76. So that means that our final answer, is going to be 2.8 to 2 significant figures, as that is where the upper and lower bound for A both match. So 2.8 is our final answer. Okay, let's look at this one here. Another exam question, exam style question. So a rectangle has a length of 18.8 centimeters and a width of 9.29 centimeters, and are each rounded to 3 significant figures. Okay, that's important. By considering bounds, work out the area, so area, important, of the rectangle to a suitable degree of accuracy, and give a reason for your answer. Okay, let's do it. So, area of a rectangle is length times by width. Let's just write that one first down. But what we need to do, as always, as this is a bounds question, is we need to work out our upper and lower bounds for our length and our width. So let's look at length first. We are told that the length is 18.8 centimeters, and they've all been rounded to 3 significant figures, meaning that our lower bound of 18.5 to 3 significant figures is going to be 18.45, and our upper bound is going to be 18.55. So I'm going to write the error interval as this. Same thing for width. So we've got 9.29 being rounded to 3 significant figures. So our lower bound is going to be 9.285. And our upper bound is going to be 9.295. Okay, so as we mentioned, area is equal to length times by width. So to work out our upper bound for area, essentially to work out the highest possible value for our area, we need to times by the upper bound of the length times by the upper bound of the width. So we're going to do 18.55 times by 9.295. And in lower bound, same thing. We're going to do for A, for area. It's going to be 9.285, the width. Should have done the length first, but the width times by 18.45. Okay. If we whack that into our calculators, so our upper bound for area, so 18.55 times by 9.295, we should get an answer of 172.4225. And then for our lower bound, we should get an answer of 171.30825. And of course, area is centimeters squared for units. Okay, so we've done the bulk of the question. Now we need to put it to a suitable degree of accuracy. So this bit here. So again, as I said, essentially what we're going to do is we're going to round both the upper bound and lower bound, and we're going to see where it matches. The higher the number of significant figures, the more accurate it is. So let's round, let's say, the upper and lower bound to 1 significant figure. We round the upper bound to 1 significant figure, we get an answer of 200. Lower bound, we also get 200. Okay, They match, but can we do better? So let's look to two significant figures. If we round the upper bound to two significant figures, we get an answer of 170. And if we round the lower bound to two significant figures, we get an answer of 170. Okay, they match, but can we do better? So let's look to three significant figures. 172.42225 to three significant figures is going to be 172 for the upper bound. For the lower bound, we're going to get 171. Okay, so they don't match to three significant figures. So our most accurate degree of accuracy for this question here is going to be to two significant figures as they both round to 170. So we just say 170 centimeters squared to two significant figures. And then we can just say as both upper bound and lower bound round to 170 to two significant figures. Excellent.